Hi guys! So the question becomes, after we've done polynomial division, how do I deal with the resulting rational function if, for example, it doesn't work with substitution or integration by parts? None of the other methods I've seen work. Well, in this case, we use something called partial fractions. And what partial fractions is, I like to think of it as undoing addition of fractions. So let's get into it to make that make sense. So let's say that I have, for example, the integral of 2 over x minus 2 plus negative 1 over x plus 3 dx. Well, that's a really simple integral. I can just immediately say this is 2 ln of the absolute value of x minus 2 minus ln of the absolute value of x plus 3 plus a constant. Really straightforward. What if, though, instead of being given it in that way, we were given it as an added fraction? So in other words, if I have 2 over x minus 2 minus 1 over x plus 3, we know how to add fractions. So I'm just going to do x plus 3 over x plus 3, x minus 2 over x minus 2. And I'm going to end up here with 2x plus 6 minus x plus 2 over x minus 2 times x plus 3 is equal to x plus 8 over x squared plus x minus 6. What if I were given this integral instead of the original integral? We have a problem because 2x plus 1 is the derivative of the denominator, and that is not equal to the numerator x plus 8. So what can we do? And the answer is, well, I already know the answer to this question because I know that this is the same thing as 2 over x minus 2 minus 1 over x plus 3. So how can I get from here back to there? And that is partial fraction. So that's the method that we are going to learn today. So our goal here is to figure out, actually we'll write this down because it's super important. Our goal here is to figure out how to turn x plus 8 over x squared plus x minus 6 into 2 over x minus 2 minus 1 over x plus 3. And the first thing that we're going to do, our step one, so this method that we're going to create right here is called partial fractions. We're going to create those steps for partial fractions together while actually doing this. So steps for partial fractions. And the first step of partial fractions is to divide if necessary. And in this case, and so this would be if the degree of the numerator is greater than or equal to the degree of the denominator. And in this case, it's not necessary. The degree of the top is 1, the degree of the bottom is 2. So here just we'll write not necessary. Now the second thing we're going to do is factor the denominator. So in this case, we have x squared plus x minus 6, and I know that equals to x minus 2 times x plus 3, two numbers that multiply to give me negative 6 and add to give me a positive 1. Then my third step is to create what's called a partial fractions decomposition. And so a partial fractions decomposition is taking the original rational function and writing it as a sum of fractions, recognizing that the only possible denominators of those fractions are the factors of the denominator that I have. So this is writing as a sum of fractions, recognizing recognizing that the only denominators are the factors of the denominator I have. So we're actually going to separate this into cases in just a minute. So we'll say see cases below. Okay, so what I have here then is x plus 8. Actually, I'll do this in black. X plus 8. I already factored, so I have x minus 2 times x plus 3. The only two factors I have in this denominator are x minus 2 and x plus 3. So what that means here is, when I'm separating this into fractions, I'm going to have a fraction that has x minus 2 as a denominator, and I'm going to have another one that has x plus 3 as a denominator. And I know there's not going to be any fraction with like x plus 5 or x plus 7 as a denominator, because if there were, it would show up in that denominator of the original thing. When we think about how we added these fractions together, right? If there had been an x plus 7, then we would have ended up multiplying by x plus 7 as well, and that would have been a factor of the denominator. So we know that these are the only possible denominators. More than that, though, our first step was to divide. So I also know that my numerators will have a lower degree than that of the denominator. So what that means here is, well, my denominator has a degree of 1 already. To have a lower degree than that, the only thing we could have on top is a constant. So I'm just going to put letters to represent those constants. We'll have an A and we'll have a B. You can put whatever letters you want. I like to spell my name or my initials. It really doesn't matter as long as you don't repeat letters. So I know I'm going to have an A and B there. And so now that I have that, my goal is going to be to solve for A and B, or in other words, I want to solve for the numerators. So here we're going to say solve for the numerators. And the way that we're going to do that, we have two different methods that we're going to learn. So we want to solve for the numerators by multiplying both sides by the original denominator. And then using either method 1, method 2, or a mixture of methods. Of both methods. And so today we're only going to see method 1. In next class we'll see method 2 as well, and we'll see like when one is better than the other. So for method 1, we're always starting here. We're going to go with method 1, and we're always starting for both methods the same way. And that is multiplying both sides of what I have up there by the original denominator. So I'm going to do x minus 2 times x plus 3, x minus 2 times x plus 3, and x minus 2 times x plus 3. So what I end up with down here is a bunch of things cancel out. So I'll have x plus 8 is equal to A, the x minus 2's cancel out, and I'm only multiplying by x plus 3, plus B, the x plus 3's cancel out, and I'm only multiplying by x minus 2. So method 1 will then have us, we'll have a step 1 of method 1. We're going to plug in x values starting with the zeros of the denominator. Actually, we're not going to call that 1. So plug in x values starting with the zeros of the denominator. So in this case, we're going to start by finding the zeros of the denominator. When I plug in -3, I get 0. And when I plug in +2, I get 0. So these are the zeros of my denominator. So these are the values that I'm going to plug in. So I'll start by plugging in x is equal to 3. I'm sorry, -3. And I'm plugging it into that equation. So I'll have -3 plus 8 is equal to a times 0 plus b times -3 minus 2. So I get 5 is equal to b times -5, which gives me b is equal to -1. There we go, we solved for b. Now, then I'll plug in x equals 2. And plugging in x equals 2, I get 2 plus 8 is equal to a times 2 plus 3 plus b times 0. So this gives me 10 is equal to a times 5, and then a is equal to 2. So I was able to solve for both of my numerators just using the simple method 1. So you'll notice it says starting with the zeros of the denominator. Sometimes that might not be enough, and we'll see that later. So our last step here is, once we have solved for those numerators, rewrite the integral and solve. So in this case, I will have that the integral of x plus 8 over x minus 2 times x plus 3, that's the integral we started with, is equal to a. And we had a over x minus 2. So this will be the integral of 2 over x minus 2 plus b, that's -1 over x plus 3 dx. And I end up with 2 ln of x minus 2 minus ln of x plus 3 plus c, and I'm done. And I got the exact same answer that I started with. So before we added them together, we had that 2 over x minus 2, we had that -1 over x plus 3. So anyway, these are the steps for partial fractions. This is how partial fractions works. In a minute, we will see what the different cases are and how this can actually be a lot more challenging than this problem was.